Hi everyone, welcome to Om Learning Lab. In this video, we are going to understand how attention mechanism works in transformers. Now, transformer model architecture, which you can see on the screen right now, was introduced in 2017 paper, Attention is All You Need. This picture has directly been picked from that paper, and we are going to cover in detail how attention mechanism works in this transformer architecture. Now, transformer architecture is the building block of LLMs, and as you all know, LLMs have taken the world by storm. In fact, transformer model architectures have also been used in computer vision problems for computer vision tasks, and many people are saying that the time of CNNs, which is convolutional neural networks, is gone. Transformer vision models are the future. Now, that being said, let's get into it and try to understand how this attention mechanism works, specifically how it works in this particular architecture. In this video, we will focus on this particular chunk, which is the encoder block. So there are two blocks. This block is the encoder. So we have inputs, as you can see, and this is the encoder part. This block is the decoder block. This is your decoder, and this is your encoder. In this video, we are going to focus on understanding how encoder works, how attention mechanism works inside encoder, and then in subsequent videos, we will explain how decoder works as well. That being said, let's get started. So let's say we have a sentence. Let's take any sentence. Let me take some random sentence like Henry likes to play football. Let's say this is just any random sentence. Now, we know that for any text to be of any use for any machine learning algorithm, any machine learning model, it needs to be converted into a vectorized format. And we have many algorithms for that. So we can use some sparse embedding techniques like TF-IDF or BM25. So BM25 is a modified version of TF-IDF, so to speak. There are lots of improvements over TF-IDF in BM25, but in many ways, it's kind of built on the similar idea or similar premise as that of TF-IDF. So these are sparse embedding methods that can be used, or we can use dense embedding methods as well, which take context information into account. So these embedding techniques are keyword based. They are known as keyword based techniques, and we can use dense embedding techniques as well, like what to wake, which is really famous, and we can use glove, whatever. So whatever be the mean, the first step obviously would be to convert each word here into its dense representation. For this particular video, I am going to represent vectors in the color green, and I will represent them by this notation. And in between, I'll just write their length. So let's say our vectors have dimension 1 cross d, vectors of d dimensions. So it can be something like 0, 0, 0.1, 2, whatever. There are just d elements over here. Pretty standard. So each of these words will be converted into corresponding vectors by passing them through any embedding model, so to speak. Once we have these embeddings, we will start our processing on them. What is it that we are going to do? So if we go back to this model architecture, once we have our inputs, we have the input embedding. There is something called positional embed encoding. We'll talk about this later. Once I have explained how attention works in encoder, we'll come to this particular point. why is it important. But for now, let's focus on the operations that are going to be done. Now, if we read the paper, there are lots of operations which have been mentioned, and a lot of them are mathematical in nature. So it's quite easy to get lost in all of them. And in fact, even if you try to understand those, it's quite possible that you don't get the intuitive meaning of intuitive reason behind why a certain operation has been done the way it has been mentioned in the paper. Now, what will happen is each of these embeddings we have, let's let's call them some embedding matrix, shall we? Let's call them some I'll represent it with some embedding matrix. So we have 5 words here, like 1, 2, 3, 4, 5. Yep. So let's just look at the first word, W1. So first row, first column, W1, 2, W1, 3, so on and so forth. For simplicity's sake, let me just assume that all the words have dimension 4. Obviously, that will not be the case. I think in original paper, they had some dimension of 512 or something. But regardless, this is just for understanding purpose. We can, of course, tweak the dimension of representation. That just depends on our choice. So let's say this is the first word in my word matrix. This is representation of Henry. Similarly, we can have representation of likes, W21, W22, W23, and W24, so on and so forth, all the way till football. So W51, all the way till W54. Let's say this is the word matrix that I have. What the paper proposes to do is, as per the paper, this matrix is called X matrix. In fact, I represented this with small w's. I could have represented them with X also. But regardless, this matrix is X, your input, the X variable. And what they have suggested us to do is, we will try to project them into 3 different forms called query, key, and value. This is query, this is key, and this is value. Now, what am I talking about? What the hell are these things? What is going to happen? Let's take a few steps back and try to understand. So, what are we trying to achieve? We are trying to achieve how we can pay attention to certain words, right? So, we want to say, let's say, for example, if someone asks who likes to play something, it's Henry. So Henry and play have some relation between them. What does he like to play? Football. Play and football have some relation between them. What does he like? Like and football have some relationship between them. I mean, each word is associated with the other words, and we can assign some weights to it, right? To represent how much importance we should give to words when we consider a particular word. Like, for example, if I'm considering play, let's say currently I am looking at the word play, and I can choose to assign weights to the remaining words. How much weight should I assign to Henry? How much weight should I assign to likes? How much should I assign to the word to? How much to play, like the word itself, and to football? That's basically what attention is doing, right? For every word, we're trying to assign weights to the remaining words to see, in the context of that particular word, how much importance do the other words have. That's what we are trying to do. So the word that we will be looking at, the word for which we will consider how much importance we should assign to the remaining words, that will be called the query. Of course, each word will become query at some point of time. So in this example, play is your query. What is key? Key is basically the remaining words with which we are comparing the current word in consideration, or the query. So in this case, all the remaining words are the keys. Okay. Now, there is a source of confusion which is possible here, that when we're first doing attention on the input sentence, do we consider all relations? Like, each word's relation with all the remaining words, or do we just consider its relation with the words that are preceding to it? The answer is, as per the paper and as far as I could understand, in the encoder section, we want to consider relationship of every word with all the other words, even with words which appear after it in the sentence. That being said, every word plays three roles. The first one is query, like I said, when we are taking it into consideration. The second role is key, that is when where key is all the other words with which we are trying to compare the current word to assign weights. And then value. Value is basically for the final attention computation. So what is it exactly that we are trying to do? What is this query, this key and value? Now, just try to pay attention here. Let's say let's say I consider the first word Henry. So this word is W11, W12, W13, W14. Now, I want to convert it into a query. Let's say the query dimension is, we can maintain same dimension here. Let's say something like 1 cross dk. There are some dimensions as per the paper. I think dk for query and key and dv for value. But for simplicity purpose, let's just assume all of these are 1 cross 3 vectors. Okay. Now let's say I want to transform this particular input word, which is the embedding for Henry, into 1 cross 3. So this is 1 cross 4. I want 1 cross 3. So I definitely need a 4 cross 3 matrix over here. Right? So I'll have some 4 cross 3 matrix. I can call it some WQ matrix. In fact, that's exactly what it is called in the paper as well. This is our query weight matrix. This can be learned by the model. We are basically projecting the input word, so to speak, into a query vector. So this is 1 cross 4, this is 4 cross 3, and we'll get some 1 cross 3 output. Let's call it Q11, Q12, and Q13. This is the query representation of the given word. Okay, fair enough. Now, let's just take some other word. Let's say I'll consider play. So Henry likes to play. Henry and play should be somehow related. And let's consider two words. Let's consider this word to, and let's consider the word play. Now, let's say, so to is the third word, play is the fourth word. So I have two more words. So W31, W32, W33, and W34. This is the representation of word to, and the word play is W41 all the way up to W44. Now I want to convert these two words, I want to project them into keys. I want to represent them as keys so that I can compare my current query, which is Henry, with them. Similarly, I'll have a WK matrix as well, and again it will have the dimensionality 4 by 3 because these are 2 by 4. So when we multiply them with a 4 by 3 matrix, we'll get a 2 by 3 matrix, and 2 by 3 matrix is what we need, right? We want the representation of the key representation of both the words to and play. That's what we had here, right? So to and play, the third and the fourth word. So this is going to be kind of mathematically rigorous because the whole point of this video is to untangle the mathematics, to avoid thinking of the entire process as a black box. So I want people to understand this thoroughly. This is not that difficult. It's extraordinary, but it's not that difficult to understand. We can do it, guys. Come on. So once I do this multiplication with this key weight matrix, which can again be learned by the model during the training process, I'll get key representations of 2, K31, K32, K33, and I can get key representation of play, which is K41, K42, and K43. Now, if I want to see how much is my current word related to these two words, the standard process would be a dot product. So I can just take a dot product between my current query and each of these keys and try to see how much are these related. More specifically, I have a 1 cross 3 matrix and I have a 2 by 3 matrix. How am I going to take the dot product? Of course, I'll have to take its transpose. In other words, let me change colors now. Here will be our first computation, which is query multiplied with keys. This is just something that I'm doing at vectors level so that it is easier to understand. I'll of course move on to a more general matrix representation which has been mentioned in the paper. But this is important to build the understanding why that works. Alright. Now, what am I going to do here is, so my query matrix would look the same Q11, Q12, Q13. And in order to take the dot product, like what is it that I'm going to do, that I want to do? I want to multiply Q11 with K31, Q12 with K32, Q13 with K33. Because I want to see how relevant is my current query in context of the given key, which is 2. This stands for 2. And this stands for play. That's what my end mission is, right? So we cannot forget the end mission. That's what we want to do in the end. Okay. Now, what we need to do is how to compute them. Like the dimensionalities are definitely different. So how do we proceed with this? We'll have to take a transpose of this matrix, the query matrix. Once we do take the transpose, this is a 2 by 3 matrix, it will be a 3 by 2 matrix, and it will look something like, K31 will remain as it is, and I'll get my K32 here, I'll get my K33 here, I'll get K41, K42, and K43. When I do take this product 1 by 3 with 3 by 2, what is it that I'm going to get? I get a 1 by 2 matrix, but there will be a lot of computation, so that's why I'm just taking some additional space. Let's see how this goes. So Q11 will be multiplied with K31. So Q11 multiplied with K31, Q12 with K32 plus Q12 multiplied with K32 plus Q13 with K33, Q13 with K33. This is the first value that we are going to get. Okay. Just a second. Just for that, let me take some additional space because this is 1 by 2 matrix, right? Okay. This is the first value. The second value will be the comparison of the query with the second key, which is for play, remember. So that will be again Q11 into Q41. People who are completely familiar with matrix multiplications may feel free to skip this part, but I'm doing this just for the sake of completeness. So Q12 multiplied with K42 plus Q13 multiplied with K43. So we got our 1 by 2 matrix, which is basically query and key multiplication, the dot product. And we want to see how relevant is it? How relevant is our query when compared with both the words? Now, one additional step that has been proposed in the paper is, these dot product multiplications that can be extremely huge. They can be huge. Okay. And one problem that we potentially might run into as we keep on doing our calculations is what we usually do is, in order to compare how similar or how related a query is to a particular key, we'll have to take softmax, right? Softmax is basically, a sort of normalization technique, and we'll get probabilities, and the higher the probability, the higher the related a particular query is to a key. It's a very standard technique. And there we take exponentials. Now here is a problem. If these values are too high and we take their exponential, the numbers might blow up. So a normalization factor is added in the paper, which is you divide it with square root of the dimensionality of your keys. Okay. This is what has been proposed in the paper, that once you do this dot product between query and key and you get this, you take a norm. You divide all these numbers with square root of dk. Please keep this in mind. So this is effectively 1 by square root of dk and the remaining matrix which we have got. Now, once we have this matrix, after all this computation, let's call this some matrix. I don't know, let's call it alpha 1 and alpha 2. I mean, everything has been done. All these multiplications have been done, and we have taken the square roots, and everything has been done. So alpha 1 is basically the relationship of the query with the first key, which is 2, and alpha 2 represents the relationship of the query with the second key, which was play. Please keep paying attention there, right? That's how we computed that this thing, right? So this query with the first key and the query with the second key. That's the entire maths that has been happening here. Once we get this, we will take softmax. So softmax is basically something like, if I try to convert this into softmax, it will be e to the power alpha 1 divided by sum of everything, sum of all the scores, sum of all the dot products, that is to speak. So what I can do is this will be summation of all the e to the power alphas. In this case, it will be e to the power alpha 1 plus e to the power alpha 2. Something like that. Why do we do this? We do this because if something has higher importance than something else and we take the exponentials, then that will be more represented. That will be more highlighted. Right? So this is basically sort of a weighting mechanism. We're trying to assign weights. That's what we're doing. So for example, in this case, let's say alpha 1 came out to be, I don't know, something like 8, and alpha 2 came out to be something like 11. Okay. Then what will happen is, one, we are normalizing them, so everything will convert into probabilities. Second, it will be e to the power 8 divided by e to the power 8 plus e to the power 11, comma, e to the power 11 divided by e to the power 8 plus e to the power 11. So this e to the power 11 has much higher value than e to the power 8, right? And this will be highlighted more, right? Because we are ultimately normalizing them. So their softmax codes, let's say, would look something like, I don't know, it can be something like 0.41 and 0.59. Let's say these were the softmax codes. I have not done this computation for people who are wondering. I'm just assuming values at random. The idea is we want to do two things. We want to normalize the scores so that we can see it in a probabilistic distribution fashion, like how much weight should we assign to each of the keys? How relevant are each of the keys compared to the query? So this could have been 3 keys that we're comparing, right? This is just 2 keys that I took in this example, which were 2 and play. Those 2 words were converted into keys and everything else was done. It could have been 3 keys as well. So in that case, we should take this softmax because it will convert it into a probability distribution whose sum will be 1. And we can literally see how much weight is assigned, how much important a key is to the given query. Okay, and exponentials will just highlight that weight. That's all. Now, once we have this, we know how much relevant a given key is in context of the query. So once I have this 1 by 2 vector, what does this represent? This basically represents the weight distribution for the given keys for a particular query. In this case, if you remember, for the query, like where did we start off with? For the query word as Henry, what is the weight distribution for these 2 words, which is 2 and play? And we went through a whole bunch of computations to arrive at this particular vector. Particularly, what did we do? We took, first of all, we projected the query vector into a query projection, multiplying it with a weight matrix, which can be learned by the model. We did the same thing with the 2 queries. We multiplied with their transpose because we have to match dimensions as well. Then we took the norm with dk, so that we do that because we are taking softmax. We don't want the values to blow up to be extremely large. After doing this computation, I mean, this is your Q multiplied with K transpose. This is Q times KT. Then we can divide it with square root of dk for the normalization purpose. Then here we are taking the softmax. So on top of this, we take a softmax. And finally, we have arrived with this 1 by 2 vector. Now, what does this 1 by 2 vector represent? It represents the importance of the two keys in context of the given query, which was Henry. Now, it should be simpler to see how this would play out on a bigger context or in a bigger sense. In other words, here I considered just two keys. I could have easily considered all the 5 words as well, right? In that case, after doing all these operations, of course, this K matrix would have 5 words in it. So here I took 2 words. So this was 2 by 4. In that case, it would have been 5 by 4, right? If I consider all the 5 words as keys, because what we have to do is to compare the query word with all the words, right? All the words will act as keys. That is the purpose of relevance comparison, so to speak. So I could have done the same calculation easily, taking all the words as keys, and I would have obtained a 1 by 5 vector in that case. Just for people who are getting confused with dimensions here, my query vector, I'm still taking just one word as the query vector, that is Henry. So it was 1 by 4. I project it onto a query vector projection 4 by 3 size, I get 1 by 3 size. And if I take 5 words, originally they would have 5 by 4 dimensions, 5 words, each of them have dimension 4. Project it onto a 4 by 3 K word matrix, which is WK, and you will get a 5 by 3 matrix. If you do Q times K transpose, it is 1 by 3 multiplication with 3 by 5, you get 1 by 5. Right, and then you take square root of dk, which is normalization, you take the softmax, and you get this particular vector, a similar vector, a probability representation, so to speak. And that can have any random values. So Henry and Henry will of course have a very large probability value. Let's say it has something like 0.33, and then Henry likes as, let's say, something like 0.1, 0.2, let's say, and Henry likes to play this as something like 0.1. Then again we have 0.15, let's say, and this sum has to be 1 because we are dividing it with the same thing, that is the rule of softmax. So we get a probability distribution, the weights, and if I sum this up, this is what? 0.3, 0.45, 0.75, 0.78, so all that's remaining is 0.22. So let's say this is the 1 by 5 matrix that I got after the entire computation. This represents the importance of each of the words in context with Henry. So of course Henry is the most important for himself, but even if that particular value has come to us, which is like, it is of not much importance because we know that every word is important for itself, but still this distribution kind of gives us an intuitive sense that where should we pay attention to? Like if the word is Henry, how much attention should we pay to the remaining words? That is the entire idea, right? What is important, what is not important in context of the given word, in context of the query. So Henry likes something, and what he likes is football. And this is the most important. 2 is the least important. I mean, intuitively speaking, if our model is good, it should learn something like this, right? The output should be something like this. This is just an example. So once we have this weight distribution, the probability distribution of the keys in relationship with the query, we will take our final step. Our final step is multiplication of this entire thing with the value matrix. Now, what is a value matrix? Let's go back to the word matrix. So this is our word vector. This is the X that we have. And we started off with taking just one word as the query, projecting it into the query space, the query weight matrix, and we got this. And for the example, I took just two words as keys and did the entire math. But in general purpose, we can take all the words and we can do the same math. In fact, I showed you the how that would pan out dimension wise, so that should be clear as well. And you'll get a final probability distribution of the keys in context to a given query. Once we have that, what we can do is we have the word matrix, right? So we have this 5 by 4 word matrix. We can have a WV, which is the value weights. This can also be learned by the model during the training phase. And we project. So this will be 4 by 3 size. So 5 by 4 multiplied with 4 by 3, we'll get a 5 by 3 matrix here. 5 by 3 matrix. We can call it something like V11, V12, V13. This would represent the value representation of the first word. Similarly, V21, V22, V23 would represent the value representation of the second word, so on and so forth, till V51, till V53. This is the value representation of the third word. Please note, that's what we are doing, right? So in this X matrix, the first row represents the first word, embedding of the first word, second represents second word, so on and so forth. And each time I am writing a matrix, rows represent words. So this particular row represents the query. Here, these two rows are present. The first row represents something, represents two. Second row represents place, so on and so forth. Exactly the same fashion. Once we project our X matrix onto the value weights, you will get this matrix, the value matrix, whose dimension is 5 by 3. Now, since we have done in this entire computation, let me start working in blue again. This entire computation has been done, giving us this 1 by 5 matrix, which is basically the weight distribution of the keys for the given query. What you can do is, quite conveniently, 1 by 5 multiplication with 5 by 3. Or the entire math that we did earlier, softmax of q times k transpose divided by square root of dk, multiply it with v vector to get a 1 by 3 vector. What that would do, intuitively speaking. So let's just do multiplication for, so this is our weight vector, this is the 1 by 5 vector, this is the 5 by 3 vector, and this entire thing has been done in context of Henry. So let's not do the computation for Henry. So we can just start assigning weights and start doing the multiplication, and we'll see how that pans out. If I do the multiplication, let me do this multiplication, this, and try to track the results, how it looks. This is important. This is the crux of attention mechanism. So what will happen? If I do the multiplication, I'll get 0.33 multiplied with V11. So 0.33 times V11. Okay. 0.2 times V21 plus 0.2 times V21 plus 0.1 times V31, so on and so forth up till 0.22 times V51. This will be the first element that I get, right? This will be the first element that I get. Similarly, so on and so forth, everything will look like this 0.33 weight, this first thing, will always be multiplied with the first word. The first word is getting the highest weight. Similarly, this 0.2 will always be multiplied with the second row, the elements of the second row, or in other words, the second word, the second key that was being compared has got this much weight, which is being assigned here. Similarly, 0.1 is for the third, and 0. So on and so forth till 0.22 is for the last word. So what that would effectively do is, so this will be the first result, then this will be the second result. I think we're going to have V12, then 0.33 times V13, so on and so forth. We'll just have a 1 by 3 vector. That is the final output after the attention layer for the given query. That is, we have successfully taken the query word Henry and we have done all the computations that was required, and we have found a weight distribution, how much attention the given word should pay to the remaining words. It should pay the highest attention to itself, that is quite self-explanatory, and then it should pay the second highest attention to V51, which is football. I think this stands for football, is it? Yes, this does stand for football, right? Because all the, like, it will just follow, right? 0.22 will be multiplied with V52, and 0.22 will also be multiplied with V53. That's just matrix multiplication. People can do that and verify themselves. So basically we are just multiplying the weights that we got after the softmax computation onto the value projection matrix in order to get how much weight should be assigned to all the words in context of the given word. So for the word Henry, you assign highest word to itself, second highest word to football. Henry and football are the most related. Third highest weight to this Henry, I think it was likes. Henry likes to do something. And the fourth highest weight is Henry likes to play. So play will get 0.15 weight, and the least is this word 2. 2 is not that relevant. I mean, this is just an example, but this is in essence what we're trying to do through the attention mechanism. That is, for any word which is your query, or you are trying to take that as a reference, you try to understand how much weight or how much importance, how much attention it should pay to the remaining words that are there in your vocabulary. So this is the entire computation that happens. This is the end result, and this will be sent to the feed forward layers. So going back to the architecture that they showed us. So far I have covered this part, the attention mechanism. So please don't worry about multi-head attention. I'll come to what multi-head attention is in the next video. I'll explain it in detail, what basically that does, what purpose it serves, right? So once we have done the attention mechanism part, we'll just send this 1/3 vector. So in our example, for every word we have 1/4 vectors. So 1/4, 1/4, so on and so forth. The representation of each word. Each of the word will be sent through the attention process that we just saw, and we'll get 1/3 representations, which will basically contain the information that for this particular word, how much attention should be paid to the remaining words. So that information has been successfully obtained through the attention mechanism process, through the attention math, and then we send them to the feed forward layers. So that's how the context information, the attention information is preserved. Right. So that is what has happened so far, and I have explained everything in context of vectors so that it's easy to see the map, and we can easily project this to matrices. So I just took one word here as the query. This could easily be all the words. So we can do this in a single go, right? So our query matrix, this can be, so we originally have a 5/4 matrix. So this might lead to some confusion. So let me do now. So this X original embedding is 5/4. Every word, 5 words, each of them have embedding size 4. And we can have WQ, WK, and WV, which are query, key, and value projections. And here I just took a single query and explained how relevance of all the words in context of the single query can be seen, but that can just as well be, we can take the entire matrix as well. So we can do entire X multiplied with WQ, which is 5/4, multiplied with 4/3 to get a 5/3 matrix, which will be the query representation of all the words. Similarly, X you multiply with WK to get the key representation of all the words, which will also be 5/3. Then you can do X multiplication with V to get the value projections of all the words, again 5/3. Then this X times WQ is your capital Q. This is your capital K. So you take Q times capital K transpose, or 5/3 times 3/5, which is a 5/5 matrix. You take normalization with dk, softmax function is applied to it, you have a 5 by 5 matrix and you have a 5 by 3 value projection for the entire input matrix, do a dot product with V. So 5 by 5 with 5 by 3, you will get a 5 by 5, sorry, is it 5 by 5 with 5 by 3? So you'll get a 5 by 3 representation. That is, you'll get a three-dimensional representation for each of the words after the attention math has been applied to it. So in other words, once you have processed, when you have done this simple matrix multiplication, each of your words have got that information regarding where they should pay maximum attention to. In this example, I just took a single word as query and showed you how much attention it should pay to the other words. That way it's much easier to understand the math, right? Otherwise it's a mess. But easily we can use matrix multiplications and generalize that to all the words that we have, and we get a final 5 by 3 vector, which is for every word the final representation after passing it through the attention mechanism, the final weight distribution, how much attention it should pay to the other words that are there in our corpus. Once we have that, we can pass them independently to our feed-forward neural network, and we can keep moving on. So this part here, I can take some other color like red. This part represented here, this is the self-attention part. We have input word corpus X, and we try to learn these matrices for projections, and we do the entire math. And here is where we compare each word to the other words and do the entire context thing, entire attention thing as explained. But after that, each of the results, like we have for every word we have a 1 by 3 representation here, they can pass through independently in the feed-forward neural network, and independent processing can be done. So that allows parallel processing. So the biggest advantage of transformer was parallel processing, and here is where that can be done. Once you have done all these computations, you have the attention weights for each of the word, that representation is there with you. You can independently send each of the word embedding or the attention weights, whatever you got as the output, to the feed-forward neural network without any dependencies involved. So it can be processed in parallel. So that speeds up computation. So that was an additional point, but this is how encoder works, and this is the output of one layer of encoder. So the first layer of encoder would get the original input embeddings for the words. That is, the first layer of encoder would get those inputs. And after positional encoding, which I'll explain in the later videos, has been done, we'll go through this entire process. This math will happen, and subsequent layers of encoder will get these outputs as their feeds, and same math will happen inside them as well, and they will send to feed forward neural network, so on and so forth. Ultimately, their outputs will be sent to the decoder, which we'll understand in the subsequent videos. But for this video, the entire idea that I wanted to put across was, we need to understand the intuition behind the math that has been proposed for the attention mechanism, how it works, why intuitively it is important, and how the internal math would look like. We shouldn't be scared by it. We should in fact learn it and understand in detail, so that we can give our contributions as well to the beautiful field. That's all for this video. In the next video, I am going to cover in detail about what this positional encoding is for and what multi-head attention does. Those are two important concepts. And subsequently, I will go to the decoder section. What is masked multi-head attention? Why is masking required? What exactly it does? And how the output from the encoder, that is, what has happened so far. For every word we have learned an attention embedding, right? So this 5 by 3 is, for every word we have some attention embedding, which will pass through feed-forward layers parallelly. All that stuff will happen. And finally, when we have the output from the encoder, what we will do, we'll have to send it to the decoder to get our task accomplished, right? So it can be any task. For example, it can be machine translation. So we'll understand in detail how the outputs of the encoder are passed to the decoder for subsequent calculations. But for this video, this is it. I would recommend people to pause the video, go through the math, check the math for themselves, refer to the paper if required, and try to do this through pen and paper yourself so that this isn't a black box for you anymore. So I hope you learned something. At least some math was clear, at least some intuition was clear. I tried my best to uh, make it understandable as much as it was possible. So thank you guys for watching, and see you in the next one.